In this problem, we have a piston assembly from an internal combustion engine. The crankshaft, OA, is rotating at a constant rate of 2,000 RPM, counterclockwise. If the piston is at top dead center position, where theta is equal to 0, determine A, the velocity and acceleration of the piston head B, and B, the angular velocity of connecting rod AB, and C, the angular acceleration of connecting rod AB. Alright, so we have a piston assembly. The piston goes up and down, whereas the crankshaft, OA, goes around in a counterclockwise fashion, and therefore running the rest of the system. Alright, so we want to find the velocity and acceleration of the piston and the angular velocity of connecting rod AB and the angular acceleration. Alright, so we want to get familiar with the system, of course, and any problem. Identify fixed points and known points of velocity. So if you look here, right, O is definitely a fixed point. Everything, the crankshaft OA rotates about it. And then that makes A go and A makes B go. But then if you look at the piston at B, it can only travel up and down. So we can use that information when we solve the problem. It cannot go left and right. Alright, so we're going to assign angular velocity directions, and we're going to start from a fixed point or a point of known velocity and move out from there. So here we would start at O, go to A, find the velocity at A. Then we go from A to B. We don't know the angular velocity of AB, but that's alright. We're going to apply the constraint that B only goes up and down to find that. And we'll follow a similar procedure for the acceleration. Alright. So here we go. We have a figure. Alright, we're going to assign the angular acceleration of OA in the same direction as the angular velocity. If we assign in a direction that's not true, we'll just get a negative from our answer. So if A goes down, B is going down, so link AB will be rotating in the clockwise direction. So we'll give that the same angular acceleration direction. Alright, so we have theta here, and then we have another angle phi here. They share a side, so in order to determine phi, all we have to do is set the signs equal. So the length of OA times sine theta equals the length of AB times sine phi. So we can always know phi if we know theta. Alright, we'll start with link AB, or sorry, OA, like we said, start with a fixed point and go to A. So we have the relative velocity equation right here. Go to A from O, we apply it, so VA equals VO plus omega OA cross RA relative to O. Alright, velocity of O is 0. We assume that OA is in the K direction, and then we just decompose the distance from O to A into the X and Y coordinates. So we have X and Y. Then we take the cross product. Make sure you look at the cross product, make sure everything makes sense to you. So K cross minus I is minus J, K cross J is minus I. Alright, we plug in everything we know, including that theta equals 0, and we get a velocity for A. Now that we have a velocity for A, we can move on to B. And we do the same thing. We go from B to A with the relative velocity equation, but we don't know what omega AB is, so that just follows through into a variable. Alright, but we know that the velocity of B only goes up and down. Right? So that we solve for, VB, only has an I component. That means the velocity at top dead center of B is 0 because there's no J component. And the I components will equal 0 because there's no I direction velocity at B. So we can also use that to determine what omega AB is. So we set the velocity in the I direction to 0, solve for omega AB, and we get a positive number. That means that we assume the correct direction. So our direction that we assumed was minus k, so we'll keep that. All right, so we follow the same procedure for the assembly. We go from O to A using the relative acceleration equation, and we plug in just like we did before, get a value for A, then we go from A to B using the relative acceleration equation, get an equation that has alpha AB as a variable because we don't know that, but we know that the acceleration of A or acceleration of B is all in the J direction, so that means it is 6,577.2 meters per second squared from this equation here. And we know that the I component has to go to 0, so therefore the acceleration of AB at top dead center is 0.